Hello, everyone. Today, I'm going to talk about how to compute cliques more efficiently in parallel. Cliques are a classic graph theoretic problem with many applications, among them in the analysis of social networks, bioinformatics, and computational chemistry. A k-clique is a subgraph which is fully connected. In k-clique listing, we are interested in enumerating all of the k-cliques. Unfortunately, for the general case, no algorithm which is better than the naive algorithm of enumerating all k-tuples is known. This is why we focus on special families of graphs which are more tractable. Now, what do we mean by a tractable family of graphs? The goal is to find an algorithm where the work to compute all of the k-cliques is linear or polynomial in the size of the graph, and it is allowed to be exponential in a parameter which only depends on the size of the clique and properties of the family. For example, in bounded degree graphs, we can compute all k-cliques efficiently. And also for planar graphs, it is well known that they do not contain any 5 cliques, and all cliques can be enumerated in linear time in planar graphs. We focus on graphs which have low degeneracy. This concept generalizes both bounded degree and planar graphs. Let's look at the following example. The graph which is drawn is a bicycle wheel graph. It has a large maximum degree. In the example, the maximum degree is 6. Now, let's try to orient the edges of the graph so that the out degree is as small as possible. In the example, we put the blue vertex, the center vertex last, and so we get an orientation where the maximum out degree is only 3. Now, if we can construct such an acyclic orientation with out degree s, we say the graph is S degenerate. And this is somehow a generalization of having a small degree. We can immediately conclude 2 things. First of all, an S degenerate graph does not contain an S+2 clique. And moreover, these graphs are sparse, meaning that a S degenerate graph with n vertices has big O of Sn edges. We are ready to consider our results for S degenerate graphs. Danish et al. Also presented an algorithm for S degenerate graphs, which has a work which is much better than naive. The work is now exponential in S/2, so it's S/2 to the k minus 2, which is the leading exponential term, and then there is a factor of the clique size times the number of edges. Unfortunately, the depth of their algorithm is linear in the number of vertices. She et al. Presented an algorithm with a different work depth trade-off. Here, the depth is only k times log n plus log squared n. However, the work is now worse by a factor which is exponential in the clique size. We present 2 bounds here, which also strike a similar work depth trade-off, but for the same depth, we improve on the work. So first, for the same depth as Danish et al., we get an algorithm which is now exponential in S+3 minus k over 2. So we have reduced the base of the exponent, and in particular, to get a feeling about what this means, if k is on the same order of s, then this is an improvement which is a factor exponential in k better. Now, for the same depth as Xie et al., we also present the same kind of improvement in the base of the exponent of +3 minus k over 2. And now notice that k is always at least 3 because we are looking for 3 or 4 cliques. Let's consider a high-level overview of our algorithm. It starts out by constructing an acyclic orientation of the graph with low out degree. And then it recursively finds cliques by extending the cliques by edges one after the other. And during this process of recursive enumeration, we apply a pruning criterion to which edges can possibly extend the cliques. And this is what gives us the asymptotic advantage, this pruning criterion. Now let's look at the bounds for the individual parts. For the acyclic orientation, we get a work depth trade-off. So either we can get an orientation which is only approximately as good as the lowest out degree orientation, and we get a low depth, or we can use the greedy algorithm, which gives us the smallest possible out degree, but a linear depth. And then for either of those two choices, we get bounds for the recursive enumeration, where you can see that the base of the exponent depends on this out degree of the acyclic orientation. Now, next, I will focus on this recursive enumeration. Let's consider an example of how we can recursively extend a clique by adding edges one after the other. We start out with a single edge, here connecting V1 and V6, and then we recurse on the subgraph induced by the vertices, which are both out neighbors of V1 and in neighbors of V6. In the example, these are the vertices V2, V3, V4, and V5. Then we continue, we pick the edge V2, V5, and we recurse on the next subgraph. Here in the base case, we see that there is no edge between V3 and V4, and hence we fail to find a sixth clique because there is no sixth clique. Now notice that we recursed on the set of vertices that are out neighbors of the first endpoint and in neighbors of the second endpoint in the current subgraph. So these vertices are sort of sandwiched in between the two edges. And by doing this, we avoid double counting. And an easy pruning rule that we could apply is if we want to find a k-clique in the current subgraph, then clearly if this community is smaller than k-2, we cannot find a k-clique in the current subgraph. However, computing this pruning rule would be too expensive. This is why we consider upper bound on the size of the community, which is the number of vertices which are ordered between the two endpoints in the order of the vertices that we get from the acyclic orientation. And this is the vertex distance. Now to compute this, we only need to maintain these vertex labels consistently when we do the recursion, which is much cheaper than computing the necessary intersections that we would need to compute the community sizes explicitly. And as we will see, this pruning criterion suffices to get the asymptotic improvement that we sought. The edges that could potentially be candidates to start a new recursive call, we say are the relevant edges. And so in the analysis, we are always looking at edges which are relevant with respect to a certain size of the clique that we are still looking for. So we say if the vertex distance is larger than C, then the edge is relevant with respect to C. And this will mean that we can still find a C clique in this induced subgraph that we are recursing on. In the example, there are two edges which are relevant with respect to 3 because they have at least 3 vertices in between them in the vertex order. And just all these edges which are relevant with respect to C are the relevant edges. Note that the C, because of our low out degree orientation, will always be bounded by the order of the degeneracy. Next, I will give you some insight into the analysis of the pruning rule. I will be comparing it with the more naive way of doing the recursion, where we iterate over all of the edges and recurse on the subgraph induced by the community of this edge. What I will be comparing is the total size of the subgraphs that we recurse on. So more specifically, the number of edges in those subgraphs. In the naive case, this means that we are summing over all of the edges, and then we have as many edges as are in the subgraph induced by the community of the edge. And this is upper bounded by n/2 squared times n. Now, if we only consider relevant edges, then we get an improved bound. So now in the sum, we are only considering edges which are relevant with respect to the current C, which is 2 smaller than the clique size that we are currently looking at. And then for the subgraphs that we are recursing on, we only need relevant edges with respect to C minus 2, because now we already have an edge, so we need a smaller clique. And here we can show with some careful combinatorial analysis that this is now upper bounded by n minus C over 2 squared times the number of relevant edges with respect to C in the current subgraph. And now this humble improvement of minus C in this quadratic term will be amplified recursively, because this was just one step. And so this is where we get the improvement that grows with K, just by bounding the improvement in one step. And then this will show up in all of the inductive proofs. Now, in summary, we have the first part of the algorithm, which is all about finding a good acyclic orientation. And this is where we get the different work depth trade-off. And then the second part is all about the analysis of a pruning rule, which gives us improved work bound. And here you saw that the C from before is what translates into the minus K in the base of the exponent. And the gamma term, again, depends on the quality of the acyclic orientation. In this presentation, I have focused on graphs with low degeneracy. In the paper, we also consider a generalization of degeneracy called community degeneracy. And for graphs of this family, we provide similar work depth trade-off. It remains an open question to find the best work trade-off in both families of graphs. We think that it might still be possible to improve the work bound for these kinds of families of graphs by maybe extending the ideas that we have. Finally, it's always interesting to consider questions of which families can we really compute cliques efficiently in.